We have two main ways to run AI models. One is online through cloud services. This usually means paying for access, but the upside is you get really powerful hardware without buying anything yourself. It's super convenient and updates and optimizations happen automatically. The downside is that your data has to be sent to the cloud, so it might not be completely private. Plus, if you use it a lot, the costs can add up. The other option is running models locally on your own computer. This is free and keeps your data completely private, since nothing leaves your machine. You also get full control over the software and settings, which can be a big advantage if you want to experiment. The downside is that it depends on your hardware. You might run into slower performance or limitations if your system isn't powerful enough. Also, you are responsible for setup and maintenance, which can be a bit more work. So really it comes down to a trade-off between convenience and power versus privacy and control. For example, music generation is pretty cheap these days and doesn't really require running models locally or setting up your own hardware. So I built Sona Music Studio web application where you can generate music and do a lot more. I generated tracks using CUDA API and as you can see each track costs only 6 cents. Since it's cheap, there is no need to run anything locally. You can generate multiple variations of song and experiment without worrying about your computer's performance. When you want to build an application using various models in the same project, the Fall AI is the best place to go. So I built a real estate application where you can stage a room, view it from multiple angles, create video and more. I use multiple models from Fall AI to make all of this possible. Let's go to Fall AI and navigate to explore and select audio to video. Let's then choose LTX 290B distilled version and let's run the demo.
LTX2 audio to video is now available on FAL. You can create avatars with just an image, and LTX2 audio to video is now available on FAL. You can create avatars with just an image and an audio, just like.
So you will see that this LTX2 is a very capable model. The input it requires are image, audio, and the prompt. But you can see that this video generation isn't that cheap, especially considering that the first video you generate may not be exactly what you want. You might need to try several times with different prompts or images. Also note that if you generate a song about 3 minutes long, most video generation models can only handle generating video in one shot for a short segment. For example, the LTX2 model works great for 20 seconds. For about 20 seconds. If you try to extend it for longer sequences, movements that were natural suddenly became sluggish or floaty. A person walking might start sliding across the ground with their legs not moving correctly. 20-second mark is the event horizon for the LTX 290B model. Because this model generates video and audio simultaneously in a single pass, it's extremely sensitive to its context window. These LTX 290B are considered powerful because they move away from the old way of gluing audio and video. Instead of generating a silent clip and then trying to find sounds that fit, they use a unified single pass. What I'm going to do is run the model entirely locally on my HP Omnibook with 32GB of RAM. You should see that the video generated will be quite different from the demo because Video generation requires a lot of compute. I'll generate 9-second video based on the track I created with Suno. Interestingly, you will see that we generated in 3-second chunks, and the next chunk understands the previous one to logically make the video coherent. This will be especially interesting for people who want to run models locally and have access to more powerful GPU, allowing them to run everything directly, say in Python code. While most local AI models are optimized for NVIDIA GPUs, CUDA, this project demonstrates how to run LTX on Intel Arc XPU hardware. This is a significant milestone as XPU support is currently rare, providing functional pathway for Intel Arc users to leverage high-performance video generation. XPU stands for Cross-Processing Unit, and it's Intel's way of abstracting hardware. It isn't the physical chip itself. It's software layer that allows frameworks to use Intel CPUs, Intel Arc GPUs, or other accelerators without changing your code. Think of it as a universal interface for Intel hardware. A GPU, like NVIDIA's, is actual hardware built for highly parallel computations. NVIDIA GPUs use CUDA, which is highly optimized and widely supported in AI/ML frameworks. In contrast, XPU is an abstraction. It can leverage Intel hardware, but the ecosystem and optimization aren't yet as mature as CUDA. PyTorch can use Intel XPU in much the same way it uses an NVIDIA GPU. You can move tensors or models to XPU just like in CUDA, and the computations will run on Intel CPUs or Arc GPUs seamlessly, giving you hardware acceleration without changing your Python code. XPU gives your AI acceleration on Intel hardware with minimal code changes, making it ideal for local experimentation and research, even if it is not yet as fast or widely supported as NVIDIA GPUs for large-scale training. The RAM of my HP Omnibook is 32 GB. When I run this application, it uses only 16 GB of VRAM. This can be seen in Task Manager and the performance in GPU, where the shared GPU memory shows about 16 GB, and this was before the update. I checked my driver version in Device Manager, and it was 6973. I read that in version 6974 and above, they introduced the shared GPU memory override feature. The feature we are looking for is called shared GPU memory override. Intel introduced this specifically to address the exact problem we are having. Local AI models needing more than the standard 60% VRAM cap. On a 32 GB system, this feature can let you allocate up to 87% of your RAM, which is about 27 GB, to the GPU. If we open the Intel Graphics application, you will not find an option to override it. Note that this is after the update, and the one before was considerably different. Updated, I navigated to the Intel Arc graphics driver page. I downloaded the driver and installed the update. And after the update, Device Manager shows version 8531, which is the version I installed. So after that, when I opened the Intel Graphics software and navigated to the Graphics tab, I saw the option to extend the memory up to 27.5 GB, and I enabled it. So after the update, I saw the shared GPU memory showing 27.1 GB in Task Manager on the shared GPU. I just saw I increased the VRAM of my HP Omnibook, but I want to make sure Python can detect it. Think of this as health check for your AI environment. Before you try to load a massive 90-bit parameter model like LTX2, you need to know if the pipes are actually connected. The script checks if Python can talk to your Intel GPU and if that GPU has enough room to breathe. Let's run the script. So device name Intel Arc 140V GPU 16GB. This is fixed string from the Intel driver that reflects the physical VRAM specification of the Arc 140V. It doesn't change when you enable memory extension. So total shared memory visible to Python is 25.42 gigabytes. This is the actual memory PyTorch sees and can use. This is larger than 16 gigabytes, so 25 gigabytes of extended memory is being used by Python. Another test is 12 gigabytes test allocation. This is a stress test, the 12 gigabytes challenge. This is the most important part. We don't just want to know if the memory exists, we want to see if we can actually use it. The script tries to grab 12 gigabytes of memory all at once. We are forcing the Intel GPU to allocate a contiguous 12 gigabytes block of memory. If the driver blocks this 12 gigabytes request, we know the system isn't ready to handle the larger LTX to model weights. So why test against 12 gigabytes and not 4 gigabytes? Testing against 4 gigabytes is definitely too low for our goals with the LTX 290B model. If you test at 4 gigabytes and it passes, it only tells that your system can handle the absolute bare minimum for basic image generation or very small LLMs. It doesn't give you any confidence for video generation. So I open the task manager and see the RAM usage is 10.6. I open the PowerShell and run the command. It's 10.6 now. So you can see that it increases all at once up to 24 gigabytes. Let's do one more time. So this proves that it passes the test. So you can see that the full AI LTX 290-bit distilled is the API hosted version. And while LTX 290B distilled FP8 safe tensors from my hacking phase is the local weights file designed to run on our HP Omnibook. Both use the same distilled 90B architecture and 8-step sampling logic. For example, on full AI, their audio to video endpoint may include hidden preprocessing layer, often using 11 labs or similar technology to ensure the audio is clean before it reaches the LTX2 model. Keep in mind that we are not building a production application, but a personal tool for ourselves. So by using the local safe tensors file, we keep costs at zero and our data entirely on our own hardware. So the main way to live in files like this LTX 290B distilled safe tensors, which is about 27 gigabytes. This is the 90B parameter transformer that does the actual generation. It works in compressed latent space, not on raw pixels. When we say the model works in compressed latent space, it means it doesn't handle every single pixel of an image or video directly. Instead, it transforms the data into smaller, more abstract representation that captures the essential features like shapes, colors, and motion patterns. Working in this latent space makes the model much faster and more memory efficient while still allowing it to generate high-quality visuals. By operating in compressed latent space, the model only needs to process the essential abstract features of the image or video instead of every pixel. This reduces memory usage and speeds up computation dramatically. That's why even with limited GPU RAM, you can generate high quality video locally without needing a massive server. So we will discuss this later, but I want to say that the process is as follows. So latents are created here at encoders layer. So then latents are adapted and aligned at connectors layer. And latents are processed and fused at transformer layer. So the analogy is like encoders, they translate languages into words, connectors convert all words into the same grammar format, and the transformer understands and reasons over them. So Intel FP8 is smaller and faster than the full model, good for consumer GPUs. But their variants are full precision versions for higher quality, but they require more VRAM. For LTX2, we use the Geometry 12B model from Google as the text encoder. The model Geometry 12B contains the original full precision weights, but it was trained with quantization await training, CAT. So CAT simulates low precision behavior during training, so the model will tolerate quantization well later. I could also use the LTX2 encoder, but in this case I use Geometry 12B instead. Here is how it fits into the pipeline. So LTX2 generates video from audio, image, and text. When you provide the text prompt, it first goes through Geometry 12B, which converts the text into embeddings, numerical vectors. These embeddings are then passed through the connectors, then into the main LTX2 transformer, which uses them to guide video generation. So Geometry 12B is responsible for understanding and encoding text, so LTX2 can generate coherent visuals that match your prompt. Video VIA, Variational Autoencoder. So video VIA is a type of neural network that helps compress and reconstruct video data. Essentially, it learns to take a video and encode it into smaller compressed representation called the latent space, and then decode it back into a video. Even a single input image can be treated as one frame video for latent encoding. The encoder part of the VIA analyzes the video and extracts the essential features such as shapes, motion, and color patterns, while discarding unnecessary details. The decoder then takes this compressed representation and reconstructs the video. The term variational means that VIA doesn't just learn a single fixed representation for video, it learns distribution of possibilities. This allows it to generate slightly different but realistic variations when decoding, which is very useful in generative models for video. In short, a video VIA is what allows models like LTX2 to operate in compressed latent space rather than on raw pixels, making large-scale video generation feasible on standard hardware. Audio VIA. An audio VIA works very similar to video VIA, but for sound instead of images or video. It's neural network that compresses audio into a smaller abstract representation called the latent space and then reconstructs it. The encoder analyzes the audio, capturing essential features such as pitch, rhythm, timbre, and tone while ignoring unnecessary details. The decoder takes the compressed representation and reconstructs the audio, or even generates new variations. In the LTX2 architecture, connectors are lightweight sub-modules that act as bridges between different input modalities such as text, audio, and images, and the core transformer model. Each modality has its own dedicated connector, like text connector, an audio connector, and image connector, which transforms the input into shared latent representation that the transformer can understand. While connectors do not contain the main model weights or perform generation themselves, they play a crucial role in conditioning the model by aligning and injecting modality-specific information into the generation process. This design allows LTX2 to flexibly combine multiple inputs and maintain coherence across audio, visual, and textual signals. The colorful bubbles here represent latent tokens that have already been encoded and are now being reformatted and routed. The transformer is positioned at the center because it's where all the separate inputs, text, audio, and the image finally meet. It doesn't process them one by one, it handles them simultaneously. This inside this purple block, the diagram mentions dual stream audio plus video cross attention. This means the transformer runs two parallel processing streams, one for what the video should look like and one for what the audio should sound like. Cross attention is the mechanism that ensures the two streams are synchronized. For example, if the text says thunder, the transformer ensures the video shows a flash of light at the exact same millisecond the audio stream produces a booming sound. The label 90B refers to 90 billion neurons or parameters in this specific model. This enormous number is why it requires a powerful setup like an Intel Arc XPU with 32 GB RAM to run locally. Most of that memory is used just to hold this core transformer block in place. The scheduler, the denoising loop. The scheduler box inside the transformer section controls the iterative refinement process. In diffusion transformer, the model doesn't create perfect video in one pass. It starts with static random noise. The scheduler instructs the transformer to loop through the data multiple times, gradually removing the noise until the video and audio become clear. The purpose of the scheduler is to control the generation process over time, running iterative diffusion steps that progressively refine noisy latent representation into meaningful structure. Finally, the core transformer is the source of the final output. Once it has finished thinking and denoising the data, it sends the refined latent representation to the decoder, which converts them into the actual pixels and waveforms you see and hear. So video via decoder, the visualizer. The video via variational autoencoder handles the heavy lifting for the visuals. As output, it receives latent tokens from the core transformer. These are highly compressed abstract representations of the data. It then performs spatio-temporal decoding, reconstructing width and height and motion time simultaneously. Finally, it outputs the actual video frame, the pixels. Audio via decoder, the sound architect. The audio via handles the auditory stream. As input, it receives its own set of 1D latent tokens synchronized with the video tokens. It then converts those tokens into Mach spectrogram. Think of spectrogram as a heat map of sound. It shows which frequencies are loud and quiet at any given moment, but it's not yet playable audio. Finally, it outputs the frequency map to the next stage, the vocoder. While the video VI handles the pixels and audio VI handles the mathematical representation of sound, the vocoder is the final translator that turns those 1D audio latents into high quality wave. Its main job is waveform reconstruction. The AI doesn't generate raw wave audio directly because that would require handling too much data. Instead, the model produces MEL spectrogram. It's a visual map of frequencies and loudness. A computer cannot play spectrogram. The vocoder takes that map and calculates the physical wiggles needed to convert it into actual sound. In the past, vocoders were often used to create robotic voices. In modern AI systems like LTX2, we use neural vocoders. These models are much more advanced. They can reconstruct 44.1 kHz or 48 kHz audio that sounds natural and human-like, capturing fine details such as the breath in a voice. Built Python application with Intel GPU support. We use PyTorch built from Intel's XPU Index, which provides support for Intel GPUs such as Arc. In this project, dependencies are installed globally. However, it's generally recommended to use a virtual environment so that packages remain isolated and do not conflict with other projects. Like the JavaScript ecosystem where Node Modules is local to each project by default, Python's pip installs packages globally unless a virtual environment is created. To simplify the setup process, an install all but script was created. This script is mainly convenience for Windows users, allowing them to install all dependencies without needing to remember the exact pip commands. It's important not to run pip install requirement txt manually. Instead, this installation should always be done using install all but. The reason for this is that requirements txt doesn't include the installation of PyTorch with Intel XP support and Intel extension. These commands must be installed from custom indexes before the rest of the dependencies. So the install all but script ensures the correct installation order. It first installs the XPU enabled version of PyTorch, then installs the Intel extension, and finally installs the requirements. Installs the remaining dependencies from requirements.txt. This sequence is necessary to ensure that the full stack works correctly on Intel Arc and other XPU supported hardware. So we run install all. After the installation, the setup can be verified by running pip show torch. Pip show the command should display PyTorch version that includes XPU support, confirming that the correct build has been installed. Additionally, you can run Python verify XPU to further confirm that the environment is properly configured and the XPU support is functioning as expected. config.py is the main configuration module for the LTX2 video project. It sets paths, CLI, arguments, and model parameters used across the codebase. It defines path to models, inputs, and outputs. It parses CLI arguments, including CPU option to run on CPU. It provides a small set of LTX2 model parameters. So the model path points to the LTX distilled FP8 model. The LTX2 components refers to the LTX2 components directory. It's a model's LTX2 components, which includes the VIA, audio VIA, connectors, and scheduler we have already talked about. If you go into each directory, you will see the VIA component consists of the config file, the architecture, and the save tensors files, weights. The other components are structured similarly, except for the transformer and scheduler. Scheduler has no learnable parameters. It's fixed procedure that determines how to step through the diffusion process. It only needs settings like step count and noise schedule, so a config file is sufficient. No weights are required. But the transformer does have weights. However, they are not located inside the transformers subfolder. Instead, they are stored in the main file, which is the LDX290B distilled FP8 save tensors. So the JAMA path points to the JAMA text encoder directory. Input image is the default input image used to generate video. And input audio is the default input audio. This track was generated by me and only 9 seconds of it are used.
Clock is ticking, I'm picking the lock of the system. The rhythm is hitting, I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision.
And there is the directory for temporary render files. Step render. When generating track, this directory is created and each chunk, like chunk 0 MP4, chunk 1 MP4, they are stored there. The folder is automatically deleted once all chunks are generated and concatenated. And the final output is the generated video. LTX2 model, LTX2 temporal ratio. It's the temporal ratio used for LTX2 and currently set to 8. This will be discussed further. Utils. So LTX2 valid frames with duration and frame rate computes a valid frame count for LTX2 from duration, seconds, and frame rate. In this line, duration is the length of the video in seconds, and the frame rate number of frames per second, 24. So multiplying them gives the total number of frames needed for that duration. So duration, raw frames formula, and raw frames value. You can see that the frame number is increasing. The formula ensures the model generates enough frames to cover the target length, so the video matches the audio in time. So based on it, we calculate the valid frames formula. The 8 in the temporal compression, the 8 is the temporal compression ratio of the LTX2 video VIA. So the architecture is built around 8 frame groups, so the frame count must satisfy n-1 mod 8 equals 0, or have a minimum of 9 frames. Otherwise, the encoding decoding is incompatible. So valid frames formula and valid frames value. So this satisfy n minus 1 mod 8 equals 0. Load audio segment is designed to extract only a specific portion of an audio file from t-start, t-end and return it as PyTorch tensor. It's optimized to use minimal RAM by processing only the segment chunk instead of loading the full file. Load audio segment is a chunked audio loader that uses FFmpeg via Imagio FFmpeg to efficiently extract the segment of audio and convert it into PyTorch tensor, keeping memory usage low. Pipeline loader. We load and assemble the LTX to audio to video pipeline. As discussed earlier, this includes the text encoder, the geometry, VIA, audio VIA, connectors, vocoder, transformer, and scheduler. After all components are initialized, we configure the device and enable memory offloading. Phase 1. In the first phase, we load the GMO model on the CPU. This approach improves compatibility with bits and bytes, reduces the risk of out-of-memory errors during quantization, and aligns with the pipeline CPU offloading strategy. In the second phase, we load the LTX components sequentially. These include VIA, audio VIA, connectors, and vocoder. After each component is loaded, we call clear memory cache to release temporary memory. This step helps reduce the likelihood of out-of-memory errors when loading the next model. In the phase 3, we load the transformer and scheduler and then assemble the pipeline. The scheduler configuration is first loaded from the JSON file. The scheduler controls how the denoising process is performed, including how many steps are used and how large each step is. Once the configuration is read, the scheduler is initialized based on it. Next, we load the transformer, which is the core model responsible for generating the video. Transformer is loaded from local weights file, and its structure is defined by corresponding configuration. Memory usage is carefully managed to ensure the model fits within available resources. The from single file method is used with local-only loading enabled, ensuring that no external downloads are attempted. Pipeline defines how the full generation process works. This code is not implemented by us, but comes from the official Hugging Face diffusers repository. So the original design and logic belong to the open source project. Our implementation focuses on loading the required models, connecting them correctly, and using the pipeline to generate video outputs. The worker script is the main entry point responsible for generating an AI music video using LTX2. It takes a single input image and an audio track and proceeds synchronized video output. Before the video generation begins, the script performs a short preparation step. First, it determines the length of the input audio. This is done by opening the file using the audio file clip, reading its duration, and then closing the file. The duration is converted into integer number of seconds so the rest of the pipeline can use it to control video generation. Next, the script informs the user by printing the detected audio length. This provides immediate feedback such as audio length detected 9 seconds, so the user knows the input was processed correctly. After that, script initializes the LTX pipeline, including all required model components, and calls the generate video function. The detected duration is passed to this function, which uses it to determine how many segments, chunks need to be generated and how long each segment should be. This script dynamically adjusts generation settings depending on whether it's running on CPU or GPU, XPU. When running on CPU, the configuration uses resolution 384 by 384 chunk durations of 3 seconds and 73 frames per chunk. The number of inference steps is set to 8, and the total number of chunks processed at once is limited to 4. When running on the GPU or XPU, the configuration changes to resolution 320 by 320 with shorter 2-second chunks and 49 frames per chunk. The number of inference steps remains the same, but the number of chunks increases to 8. The distinction exists because GPUs are faster but constrained by VRAM, which is typically around 25 GB on devices such as the Intel Arc GPUs. By lowering resolution and chunk size, the script ensures that the model fits into memory and avoids out-of-memory errors while still benefiting from faster computation. Once the configuration is set, the script prepares the pipeline inputs. It includes the starting image, a fixed text prompt describing a realistic person singing, and a negative prompt to reduce artifacts such as blur or incorrect anatomy. Additional parameters such as resolution, number of frames per chunk, frame rate, and inference steps are also defined. So the audio corresponding to the current chunk is converted into a tensor and passed into the pipeline through pipe quarks. The pipeline then processes the image, text, prompt, and audio together to generate both video frames and synchronized audio for that specific segment. After generation, the encode video function converts the raw video frames and audio tensors into standard MP4 file format. This step ensures that the output can be easily played and shared. Because LTX2 can only generate short video segments, the full video is created by chaining multiple chunks together. To maintain visual continuity, each new chunk uses the final frame of the previous chunk as its starting frame. For example, the first frame of chunk 1 is the last frame of chunk 0, and this pattern continues for all subsequent chunks. This approach ensures smooth transitions between segments and prevents visible jumps, resulting in coherent and continuous final video. We will run the application to generate video by passing both the image and the audio segment that I generated using Suno.
Clock is ticking, I'm picking the lock of the system. The rhythm is hitting, I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision.
We will generate chunks, and once successful, those chunks will be concatenated to produce the final video. This time we will run the application on the GPU. When I run the application on the GPU, I encounter an XPU out-of-memory error when the rendering phase begins. Based on the approximate VRAM usage, the issue appears during chunk generation. Although gem is loaded on the CPU, during the rendering of each chunk, it's temporarily moved to the GPU to encode the prompt and then moved back to the CPU. PyTorch allocates about 25 GB of VRAM during rendering. which is not enough for the full pipeline. Although we hit an out-of-memory error at the end of the GPU, it's still valuable to observe how the application runs and how VRAM usage grows during the transformer denoising step of rendering. To demonstrate the application, I will record the desktop using my phone to save system memory instead of running a recording application on the computer. From time to time, I will pause the recording since some steps such as JAMA with loading can take 3 to 5 minutes. I will restart my notebook and begin recording from the start using my phone. I'm going to start the application and open the task manager. So it's running on the GPU and the audio length is 9 seconds. In phase 1, we load the JAMA weights on the CPU. Phase 2, we load the LTX to components, VIA, audio VIA, connectors, and vocoder. At phase 3, we load the transformer and scheduler and assemble the audio to video pipeline. So all components are initially loaded on the CPU. Each component is moved to the GPU only when it's needed for execution and then moved back to the CPU afterward. Note that no GPU increase in this phase. So the names represent the model's internal structure. They indicate which block or layer and projection each weight belongs to along with the FP8 quantization scales. So we are now on. So the models are now running on the GPU. We are going to render 5 chunks each with length of 2 seconds. So rendering the first chunk. This 0.8 progress bar corresponds to the denoising phase. The transformer uses 8 denoising steps and the bar tracks the progress of these steps. The scheduler determines which timestamp to use for each step. For example, step 1 timestamp 1.0, etc. After 8 steps, the noisy latents are transformed into the final video latents. Now you see that VRAM usage increases rapidly. VRAM spikes during the transformer denoising because the 90-bit transformer is loaded onto the GPU at once and it operates unload video and audio latency, which together consume most of the available VRAM. So in the end we receive an XPU out of memory error. So the GPU has about 25 gigabytes of VRAM and PyTorch was already using almost all of it. When it tried to allocate an additional 256 megabytes, there was not enough for memory, causing the XPU out of memory error. This time we'll run the application on the CPU by passing the CPU flag. Like in the GPU case, we load the gem await, LTX to components, transformer and scheduler. It's the same. The difference is that this time we are going to render 3 chunks, each with a length of 3 seconds. So I'm going to pause it from time to time, as overall rendering takes around 2 hours on the CPU. Rendering the first chunk. So we are rendering the first track. But note that there is no GPU increase at all, so as we are running entirely on the CPU. We are still rendering the first chunk. We just finished rendering the first chunk. So we are encoding the video, and you see that we're encoding, and you see that the first chunk is generated onto the project's temp render folder. So now we are rendering the second chunk. We are about to finish the second chunk rendering. Encoding the chunk, and the second chunk is generated. Rendering the third one. So all three chunks have been generated, as well as the final video. When chunks are generated, they are deleted at the end after the final video is created. Before deletion, I copied them back into the temp render folder so you can see them along with the final video. So this is the original picture, and this is the original 9-second MP3 segment.
Clock is ticking, I'm picking the lock of the system. The rhythm is hitting, I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision.
But we can run each track, we can run each chunk, and then the final video.
Clock is ticking, I'm picking the lock of the system. The rhythm is hitting. I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision. Clock is ticking, I'm picking. Clock is ticking, I'm picking the lock of the system. The rhythm is hitting, I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision. Clock is ticking, I'm picking the lock of the system. The rhythm is hitting, I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision. Clock is ticking, I'm picking the lock of the system. The rhythm is hitting, I'm flipping the script and they missed them. I'm back in the kitchen, igniting the friction with vision. An engine of precision, I'm making the lethal decision.
As you can see, we didn't achieve production level output, as it requires significant computational resources. However, we demonstrated that the LTX model can run locally on our own hardware. Despite encountering memory limitations and not yet reaching production quality results, we gained valuable insights into how the pipeline operates, including how models are loaded and offloaded between the CPU and GPU.